Değerli katılımcılar, sevgili arkadaşlar, bizi tüm sosyal medya platformları üzerinden izleyen bilim dostu, bilgisever, güzel insanlar. Herkese iyi akşamlar. Dünyayı ve ülkemizi saran COVID-19 salgınının hayatımızı her alanda zorlaştırdığı bir dönemde daha bir yılı geride bırakmak arifesine yaklaşmaktayız. TÜBİTAK Temel Bilimler Araştırma Enstitüsü önceki yıllarda başlattığı üst düzey bilimsel faaliyetlerini 2020 yılında da giderek artan heyecanla ve dünya bilim camiasına daha fazla açılarak devam ettirdi. Bu faaliyetler temel bilimin çeşitli alanları ile disiplinler arası alanları kapsarken toplam 6 ayrı ilham verici seminer serisi ile bir bilimsel Türkiye popüler konuşmalar serisi şeklinde sınıflandırılarak gerçekleştirildi. Ayrıca bu faaliyetler Nobel ödüllü bilim insanları başta olmak üzere dünyanın en önde gelen üniversitelerinden lider bilim insanlarının katkıları ile gerçekleştirildi. Bu akşam yine bu vesileyle bir araya gelmiş bulunmaktayız. Ve bu yıl için sonuncu 41. seminerimizi gerçekleştireceğiz. Ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Bu akşamki seminerimiz kimya bilimleri seminer serimiz kapsamında ve ABD'deki Stanford Üniversitesi'nden çok değerli bir bilim insanı Dr. Johannes Voss'un katılımıyla gerçekleştirilecektir. Johannes Voss, yüzey ve malzeme kimyası için birleştirilmiş deneysel ve hesaplamalı verilere dayalı tahmin modelleri konulu bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear Johannes, dear participants, dear colleagues and friends, a very warm hello everyone. It is my distinct pleasure to inform you that this evening we have another wonderful episode of the inspiring online chemical sciences seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences, relying on the unifying feature of science for humanity. It is also my sincere pleasure that I have the honor of introducing our tonight's very special speaker and leading scientist, Dr. Johannes Voss from Stanford University of United States. He has kindly agreed to join us for this seminar and is going to give a great talk, Predictive Models for Surface and Material Chemistry from Combined Experimental and Computational Data. Johannes Voss is the data science task lead at the SANCAT Center for Interface Science and Catalysis at SLAC National Laboratory and Stanford University. The research of his group is focused on the atomic level understanding and computational design of systems of relevance for renewable storage and conversion of energy. His team employs data scientific approaches to improve the predictive power of supercomputer simulation for chemical reactions with emphasis of heterogeneous catalysis. Johannes Voss received a doctorate degree from Technical University of Denmark in 2009, followed by postdoctoral works at Cornell University between 2009-2012 and Stanford University between 2012 and 2013. He was an associate staff scientist at SLAC National Accelerator Laboratory between 2013 to 2017, and with promotion to full staff scientist in 2017. With this, I want to invite Johannes Voss to the stage to begin his talk. Johannes, good morning. We are very honored to have you with us. Please begin your talk.
Thank you very much for the very kind introduction, Alikram. Thank you for the invitation. Thank you to the audience for tuning in. It is my pleasure to be speaking to you all tonight. And let me share my slides. And before I begin, I'd like to, I appreciate that the audience of the seminar series is from a broad range of scientific expertise. So my talk is going to have plenty of introductory material and then a few of my own research examples. And since there still might be a lot of information to take in, there is this no, not a pen, pointer, laser. There's this QR code here that you can scan with your smartphones, and it will lead you to a short web page just with a list of links of references that are used in this lecture, and also with further reading material like good relevant review articles in case there are certain topics here that spur further interest to you. And I'll put this QR code back up at the end of this lecture. I'd like to start off by bringing a few examples of why atomic level first principles materials design is so relevant, for example, for heterogeneous catalysis or for renewable energy materials. Shown here is the development of the world population for the last 100 years or so. And in red color is shown the fraction or the estimated fraction of the world population that would not have food if it wasn't for synthetic fertilizers as produced by the Haber-Bosch process. And one can see that ever since the Haber-Bosch process was invented, the amount of the fraction of the estimated fraction of the population that depends on it has continuously increased. And nowadays it's an estimated 50% of the world population that is the nutrition of which is sustained by synthetic fertilizers. And so this is really a very relevant catalytic reaction. And it's, for example, also estimated that every other nitrogen atom in a human body has seen such a Haber-Bosch catalyst. And this scientist here is neither Haber nor Bosch. This is Alvin Mitash, who did about 20,000 experiments on 3,000 catalysts to optimize the catalyst in the Haber-Bosch process that is used to split N2 that is taken from the air to then react it later down the process with H2 to form ammonia, the fertilizer. So there really an enormous amounts of experimentation being done here to optimize a catalyst that is in principle still very similar to the one used today. So really amazing work. Nevertheless, let's see what theory can do here. So here's now a small figure where the conversion rate to the desired ammonia catalyst per second was predicted with first principles atomic level computer simulations. On the y-axis, there's an energy axis for the transition state on a step surface side, which is the active site on these transition metal surfaces for this reaction. And on the x-axis, there's the adsorption energy of nitrogen atoms. And it's clear already from this figure that iron and ruthenium of these elemental catalysts shown here that to be predicted to be the best catalyst that you have here on this plot. And indeed, these are the two materials that are the basis of the catalysts that are in use today. And there's ongoing research, though, how one can improve upon this process that was already optimized by Alvin Mitash 100 years ago. And that is that the Haber-Bosch process requires very high temperatures and pressure, so that fertilizer can really only be produced in big industrial plants. And ongoing research is there to enable to do that in a distributed fashion on farms, so that only the fertilizer that is needed to fertilize the soil there is produced. So ongoing interesting research. That's one direction. Another relevant and globally relevant field where first principle simulations are important are renewable energy storage materials. And one important example is there that with new kinds of batteries, one could really enable a mass electrification of light road vehicle transportation, so really replacing gasoline-powered cars. And an active research direction there is to consider to replace the flammable liquid electrolyte in conventional lithium-ion batteries with solid ones that cannot burn, and that also allow for a lithium metal anode, therefore much lighter batteries. And what is shown here at the bottom left now is a result of considering over 10,000 materials and performing over 1,000 calculations on them to find new such solid electrolytes for use in batteries. And on the y-axis here is a predicted computed stability window. And in any kind of computational material screening study, it's always important to consider if a material is stable or not. I mean, it is important that these hypothetical compounds that are tested on a computer, that they can actually be made in a laboratory. Or really, in this scenario, for practical relevance, they must also be, one must be able to produce them also on an industrial scale and at reasonable cost. So stability analysis is always an important component of any computational materials design. And on the x-axis are predicted phonon energies, which are here interpreted as the mobility of lithium ions in the lattice throughout the material. So this is a way then to estimate which materials can conduct lithium ions very well, which is of course important for a good electrolyte. But besides doing high throughput screening studies, another application of such first principles applications actually to understanding a given material in more detail. For example, here is shown a time-dependent simulation study of ionic migration through another solid-state lithium-ion conductor, where it was found that surprisingly not only lithium ions are mobile, but also anions, which is not good. So that was an important finding. And so there are several opportunities why, or reasons why atomic level materials design is so important and so promising for finding materials that are addressing many relevant problems that society has worldwide. One of maybe the most frequently used methods, or maybe the de facto standard for electronic simulations, atomic level simulations in material science, is density functional theory. And so here I'm now going to spend some time of introducing it. And it is the de facto standard because of a favorable complexity versus accuracy trade-off. So a favorable trade-off versus of computational efforts versus accuracy. And so starting with the Schrödinger equation, H psi equals E psi, there are really two fundamental theorems that DFT is based on. The first one states that the energy or the total energy is a unique functional of the single particle density. And the second one then states, so that's a variational statement, that one then can minimize this total energy function with respect to the density, and the minimum is given for the ground state density. So these are two very important fundamental theorems that have relatively simple mathematical proofs. And what this effectively means is that one goes away from a wave function description of the problem, which is very complex, to a single particle kind of a single particle density description, which only depends on a single 3D coordinate, or maybe times 2 if it's electrons with a spin. And shown here, for example, to the right is the charge density simulated for a single water molecule. And with a typical high accuracy grid, 3D grid to represent such a density on, storage for that, or like amount of RAM needed, computer memory for that is on the order of megabytes. So there are 8 electrons in the system, and if you would consider the full many-body wave function, where you need to describe the probability to find an electron independence of all the other 7 electrons, then the amount of memory one would need to store that for this particular system with a similar grid now also for the wave functions would require 10 to the 40 more, 10 to the 40 more memory to store that. So intractable already. I mean, that there are wave function methods that make wave function problems tractable. So not really dealing with the full many-body wave function, but still, like the density function theory approach means a tremendous simplification. If one, for example, to study a less trivial system than a water molecule, maybe something with hundreds of electrons, which is easily possible with DFT nowadays, if the full many-body wave function of that, just a number of bits to represent that, would require more than there are atoms in the universe. So just showing how exponentially hard and untractable a full many-body wave function approach would be. But DFT up to this point doesn't really provide us with a recipe yet how to compute anything based on the density. And here the Concharm formulation comes into play. So in the Concharm approach to DFT, one replaces the interacting problem of electrons, for example, with a non-interacting one, a fictitious system that has the same density though. And with that transformation, one then arrives at an effective set of single particle-like equations where there is a non-interacting kinetic energy term, an external potential, here typically given by the Coulomb potential of the ions in the system, an average electrostatic potential term, and an up to now unknown so-called exchange correlation potential. And it's the exchange correlation energy here that corrects for all the simplifications being made, like the simplification of dealing with a non-interacting system instead of a fully interacting one. So up to here, this approach is exact. So if one only knew how to formulate this this exchange correlation energy exactly, then this is an exact theory. But in practice, one needs to make approximations to the exchange correlation energy, or the functional of the density functional for that. And later in this lecture, I'll show some research examples from my group where we use machine learning or data scientific techniques to arrive at approximations for this exchange correlation energy. Now to make use of density functional theory, what one typically assumes or takes advantage of is the so-called Born-Oppenheimer approximation that is based on the fact that nuclei are much, much heavier than electrons. And that means that a separation of nuclei and electronic timescales is possible. And one then assumes typically that when the ions move or the nuclei move, that electrons can adiabatically follow that, and they basically on a much faster or immediate timescale relax back to their new ground state density. And that means that there's a potential energy surface given by the electronic DFT solution as a function of the ionic coordinates. And it's a cartoon of that here shown to the right, just a 2D toy problem. potential energy surface. And then furthermore, it is typically a good assumption that the thermal de Broglie wavelength of the nuclei is so short that on typical interatomic distances that the coherence between the nuclei is lost. Hydrogen, which is very light, can be an exception, but typically one can assume that coherence is lost so that one doesn't need to solve any Schrödinger equation explicitly for the ions themselves. So there's no DFT on the ions. There's only really DFT being performed on the electronic degrees of freedom. And one basically thereby arrives at such semi-classical equations, which look a lot like Newton's law of motion, where the potential energy, though, is solved quantum mechanically for the electrons. And this is the basis of many of the important chemistry simulations that are done with DFT. So, one can take such a potential energy surface, subdivide it into a space of an initial state where the reactants are, a final state where the products are. Then there's a dividing hyperplane, the transition state, and based on these energetics, one can then make estimates of reaction rates. One can also go beyond this and not follow a particular path on the potential energy surface, but one can also compare different potential energy surfaces to each other. So one can, for example, take a lithium atom out of lithium metal and see how much energy it takes to put it as an ion into electrolyte in a battery. So with that, one can calculate, for example, how much voltage one can get out of a battery, what the energy profile of ions is over the battery, charge profiles, and so on. So very relevant for that field of research. And one can also very generally calculate relative phase stabilities of products and reactants of solid phases and molecules, and taking appropriate entropy terms into account, one can also deal with finer temperatures there. One can also make predictions that are actually based on these Kohn-Sham single particle-like solutions. So if one takes the spectrum that comes out of that and applies so-called quasi-particle corrections to it, then one can actually interpret those energy levels as electronic or optical spectra, shown here for a material of relevance for photovoltaics. And it's relevant because as confirmed here by the simulations, it has a direct band gap, meaning it's the valence band maximum and conduction band minimum are at the same point in the Brillouin zone. And it has a band gap that is almost ideal for absorbing the natural sunlight spectrum. And then what was shown here, that one can then go ahead and compare this to experiments and see also and understand the effect that pressure has on such systems and understand the phase transitions that are observed experimentally. With similar spectral simulations, and that this is particularly relevant for the National Laboratory SLAC where I work at, one can also simulate the effect of X-ray spectroscopy, where core electrons are excited and they then probe the valence or conduction band structure, with leaving typical signatures of, for example, as shown here, of different adsorption sites on a surface or intermediate reaction states. But this information is so complex that it's hard to, or it's almost impossible to distinguish what states are observed directly from the experimental spectrum. And here, such first principle simulations are indispensable in guiding experiments and understanding which reactions were observed with X-ray lasers, for example. And finally, another example of what DFT can do is it can also predict electronic properties out of equilibrium, like electronic transport. Shown here is the example of thermionic emission from a hot metal surface, where hot metals can escape the metal surface and they're then collected at a cold anode. And with that, for example, you have a device to directly convert heat into electricity. Shown here to the right is a comparison of such simulations of predicted thermionic current densities versus temperature to experiments, and another example where theory can explain experiment, or reproduce experiments very well. Although for this example, one really had to go quite a few years back in history to find actually such experiments being done. Then if one has established that such an approach works so well on a few experimental benchmark cases, one can of course go ahead and do something high throughput, screen for many possible, for example, coatings of tungsten to lower its work function to make it a better emitter. And at the same time, as I mentioned before, always important to check for stability, and at the same time also optimize for stability, which is something that was achieved here. And now these were now a few examples of what one can do with DFT in general. Now I'd like to switch gears and talk a little bit about data science and machine learning. So there's now a growing number of databases which store increasing numbers of really high quality first principles computer simulation results, both for material science and for catalysis. And already just that this data is stored there so conveniently, and it can be queried very conveniently. Like, for example, one can say, need a band gap in this range, chemical stability, electrochemical stability window of that range, and these databases then already can give quite a few compounds that might be exactly delivering on those targets. So that is already very useful. But now that there's so much high quality and consistent data available, of course, it also enables training of machine learning approaches. So one new promising approach is, for example, to train so-called generative neural networks, where as an input, one has a desired materials property like a band gap, for example, and then the generative AI goes ahead and comes up with hypothetical crystal structures that should have such a band gap. So it's kind of really solving, or has the potential to solve an inverse design problem. Desired property, what crystal structure would give that? And maybe a more traditional application of machine learning here is to actually replace DFT, to take these large data sets, train machine learning on them, so that one doesn't actually need to run DFT simulations anymore. DFT is very efficient, but it still requires supercomputers. So if it has a machine learning model that gives similar quality results much faster, one can then go ahead and study larger systems. So one can consider time-dependent simulations with much longer timescales than what are accessible with DFT directly. And finally, and this is a direction that I'm going to talk about a little later here in this lecture, one can actually also go ahead and use machine learning to improve the approximations within DFT itself, or generally to improve accuracy of the simulations. And there, what I'm suggesting here is to not only base this on these computational data sets, but to actually also involve experiments, because there's a number of properties where there is no higher level than DFT theory benchmark that could guide us. So therefore, there's a few cases where high quality experiments are crucial. So before I go into that machine learning part, I'd like to spend some time on the unknown part of the DFT functional that needs to be approximated, the exchange correlation energy. So as a reminder, it's this exchange correlation energy functional that is the to be approximated part that corrects for all the simplifications being made in the Kohn-Sham approach, such as having a non-interacting kinetic energy only and similar things, and average electrostatic interactions. And so quite generally, this exchange correlation energy can be written as an integral over the charge density, the electronic charge density, times an exchange correlation potential, times an exchange correlation energy density per particle. And this exchange correlation energy density per particle, again, is given by this Coulomb-like integral, where this H Kohn-Sham is the so-called Kohn-Sham exchange correlation hole. And why this is called a hole can be understood from this plot down to the left here. It's shown that for simplicity, only for the case of exchange interactions and for the case of an homogeneous electron gas, because then there's a simple analytical expression that is plotted here. So on the x-axis, there's the distance to the electron that creates the exchange hole. And at zero distance, the exchange hole has a value of minus 1/2 the density. And the reason that this is minus 1/2 and not minus 1 is that only equal spins participate in exchange with each other. So that's why it's only minus 1/2. But the fact, that is negative. So the electron is digging out an exchange hole of opposite sign that then decays with increasing distance from the electron. And generally, now there's then a adiabatic connection approach that allows one to finally connect the non-interacting case to the fully interacting one. And in that connection, the Kohn-Sham exchange correlation hole is then given as an average over the interaction strength going from 0, lambda equals 0, which means no interaction, to lambda equals 1, which is full interaction, and which allows one then to make certain deductions about what properties such an exchange correlation hole must have. And one important property it must have is the so-called sum rule. So if you take an exchange correlation hole, no matter what the interaction strength is, so it's not only applying, this rule is not only applying to the Kohn-Sham interaction hole, but it's also applying to the exchange correlation hole at any interaction strength, that it must integrate to -1. So an electron digs out for itself an exchange correlation of exactly of opposite charge. Or you could also say that in the exchange correlation hole, there's exactly one charge missing, irrespective of the interaction strength and irrespective of where the electron is. So this is an important sum rule, and it was indeed realized at some point in trying to make improvements to exchange and correlation at the squared, that it's very important to fulfill a number of these analytical rules. And really first big success in exchange correlation functional development were the so-called generalized gradient approximations, which indeed fulfill the sum rule. And they depend at each point in space on the density at that point and then the absolute gradient at that point. And it's a generalized gradient approximation because it's not a plain Taylor expansion. Those typically don't fulfill the required analytical constraints so that the functional works well. So it's a generalized one that can have more general dependence on these gradients. And the exchange part then specifically, which is something I'm going to focus on here, is written or can be written as the exchange energy of a homogeneous system times the density times an exchange enhancement factor. And this exchange enhancement factor is plotted here for the very famous and very widely used PBE GGA, where it is assumed that when the so-called reduced density gradient is 0, so there's no density gradient, that the system locally behaves like a homogeneous one, and therefore the enhancement is 1. So the exchange energy locally will be then be the same as the one of a homogeneous system, while for increasing gradients, the exchange is scaled up, so it's enhanced, hence the name of this function. And a general drawback of these GGA approximations is that they typically describe some properties well at the sacrifice of describing other properties worse. So showing in this simple plot here is the error, average error with respect to benchmark experiments for chemisorption energies versus lattice constants. And one can see that a function like PBE sol, like its name is already indicating, is very good for lattice constants, but it performs awfully poorly for chemisorption energies. And the other way around is true for the revised PBE, which was designed to be good for chemisorption energies, but it's at the price of poor lattice constants. PBE is somewhat a compromise. That is also part of the reason for its popularity. But for example, for the application of catalysis, this is kind of not satisfactory, because in catalysis one needs to describe surface reaction energetics well, but one also needs a good description of the bulk catalyst structure. So one needs something better. And what can help here are the so-called MetaGTAs. And these MetaGTAs, such trade-offs in accuracy are not necessary. And that is achieved by now having the exchange correlation energy functional also depending on the non-interacting cone charm kinetic energy density. And from this kinetic energy density, one can then now deduce at every point in space approximately what kind of chemical bond one finds oneself in. So is it a metallic bond? Is it more of a covalent bond? And therefore then the functional can adopt to that bonding scenario, like being more bulk-like where necessary, or being more surface bond-like where necessary. And for the exchange part of these MetaGTAs, it then means that this exchange enhancement factor is not only a function of the gradient, but also of a reduced kinetic energy density parameter. And the exchange enhancement factor of a very famous MetaGTA, the scan functional, is shown here. So it's plotted here versus reduced kinetic energy parameter and versus reduced density gradient. And what we can already note here is that in the simple GGA cases, it's typically that the higher the gradient, the larger the exchange enhancement. This is not true for the scan functional. So there, starting from a certain gradient on, actually exchange enhancement decreases, and it eventually goes to zero at infinite gradient. So this is very special. And this scan functional has been designed entirely based on very strict analytical constraints and norms, and it performs exceptionally well for bulk energetics, bulk lattice constants, also a number of molecular reaction energies. So it's a really well-performing functional. If one then goes to look at what happens with surface reactions, indeed these MetaGTAs can easily be constructed to both give good lattice constant and also, for example, describe a number of surface chemical bonds well. That was achieved here by us for chemisorption energies of hydrogen on late transition metal surfaces, as is shown here in this plot, comparing to experiments where surface scattering experiments of deuterium on copper are compared to simulations showing that a new meta functional we made here works very well. Surprisingly enough, the scan functional, in contrast to its outstanding performance for other properties, does seem to be the worst function here. So rises the question of which functional should one use for surface chemistry simulations. So this is kind of misleading. So we went ahead, or at least confusing initially. So we went ahead and benchmarked a number of density functional theory approaches and also higher levels of theory against high quality experimental benchmarks, where from the literature we have both numbers for chemisorption energies on transition metal surfaces and also for physisorption energies on transition metal surfaces. And shown here on the x-axis is the average error with respect to experiments in terms of chemisorption, and the average error on the other axis, on the y-axis, there's the average error with respect to physisorption. And the perfect functional would be down in the lower left corner here, showing no error basically with respect to those benchmarks. But of course, in practice, there are of course appreciable errors, and of the functionals that we have tested here, there are a few surprises. I mean, what is not surprising is that the RPBE function is very good for chemisorption, not good for physisorption, and the other way around. Like typically, van der Waals function is of course good for physisorption, but it's unfortunately strongly overbinding for chemisorption, or not surprising. What might be surprising at first is that a higher level of theory method, like a screened exchange functional, which also comes at a higher computational cost, like the HSEO6 functional, that actually does not seem to lead to particularly good predictions of chemisorption energies. And we found that is due to the fact that even though the exchange interactions are screened, that still, in the case of magnetic metal surfaces, that exchange interactions are still exaggerated, leading to exaggerated magnetic moments that adversely affect the prediction of chemisorption energies. So that's unfortunate. So in some sense, it's if one is in particular dealing with magnetic transition metal surface, it might not be quite worthwhile to pay the extra cost of a hybrid functional because it actually deteriorates the description likely. To some degree, unfortunately, this is even true for the scan functional. Also there, not quite to the same extent, but also there it turns out that to some extent exchange interactions are exaggerated, also leading to somewhat enlarged magnetic moments beyond what they should be, also in terms of some more qualitative band structure analysis, also leading to somewhat worse chemisorption energies compared to, for example, the general purpose PBE, as you can see here. So we were, of course, surprised by that, but this inspired us to go ahead and take ingredients from the scan functional, which are analytical constraints, and combine this with data science to train a new functional which combines this world of exact constraints with empirical data, so we can arrive at a functional that is good both for description of bulk structures and other relevant properties and surface chemistry. And we call this approach the MCML approach, where the acronym stands for multi-purpose constrained machine learning approach. And we use several ingredients for this approach. So there are physical model constraints that are like a subset of those applied to the scan functional. And we use the same flexible meta-generalized GGA space of exchange enhancement factors, where there's a lot of degrees of freedoms that can be optimized. And we combine this then with training data that are based on high quality experiments and also on higher level quantum chemistry training data that is in principle numerically exact. So such quantum chemistry training data does not typically not exist for solids or surfaces. So this is typically gas phase data, but this is very relevant data to include in our training. So how this works then is that we have an initial guess for a meta-GGA functional that we implement in the DFT code, and then we calculate about 700 different systems to which we have benchmarks. Those are then at fixed density trained against, so that the exchange functional is updated so that it would yield better predictions. And this new functional is then fed back into the DFT code, run these 700 systems again, so that again new predictions can be made and the function further optimized. So DFT is a very efficient first principles approach to electronic structure prediction, but it's still too slow that one could do any training of the function on the fly. So that's why we do this intermediate step of predicting new energetics on a fixed density. That's very efficient and can be done on a laptop basically. But then it means we have to iteratively rerun DFT calculations with incrementally updated functionals that then eventually converge to the desired functional. And in terms of the constraints, what we take there is the homogeneous electron gas limit. So it is well known that to describe solids well, it's important that when one is in a gradient and kinetic energy regime that resembles a homogeneous system, then it also should yield the exchange energy of a homogeneous system. And that's what the first line represents there. Exchange enhancement of 1 means there's no enhancement. So homogeneous electron gas. On top of that, to get good elastic properties, as is described with indicated with the cartoon there, one also needs to describe the perturbation around that homogeneous gas limit well, and we recover that by properly having a curvature there that it matches the analytical exchange gradient expansion. So now as I mentioned, a big advantage of the meta functionals is that there's this kinetic alpha parameter that can basically detect locally which kind of bond one is in. So an alpha equals 0 means one is basically in a single orbital system. And maybe one of the most famous textbook single orbital system that one learns in quantum mechanics classes is the hydrogen atom. And of course, it has also a pen and paper solution to it. But if you actually do DFT on a hydrogen atom, although there's only one electron, DFT still computes an electrostatic energy for it, which is entirely a self-interaction error then, and also an exchange energy to partially compensate for that. So what we can do here in this approach is actually we can choose the exchange function so that it exactly cancels the spurious self-interaction of the hydrogen atom as one of the analytical constraints. And beyond these constraints, there's also some bounds. So the exchange enhancement should never be negative, and it should also never overshoot the so-called Lieb-Oxford bound of 1.804. Our training data consists of a number of reference data. So we have experimental data from literature for chemisorption energies and physisorption energies on surfaces. Then there's a number of gas phase reaction energies, which are both from, in principle, as close to numeric correctness as possible in terms of gas phase reaction energies. And there's also a few high quality experimental numbers in there. Then for solids, we have experimental energies on what energy is gained by forming a solid from individual atoms. There's also a zero temperature corrected data for experimental data for lattice constants, and also for bulk moduli. So how fast the energy of a solid changes when when the lattice constants are rescaled. And on top of that, there's then some high quality quantum chemistry calculations of non-covalent interactions, where, for example, like big molecules are interacting via van der Waals forces. So those are very important training systems for dispersive forces on top of the physisorption energies on the surfaces. And with that, and after a few cycles of DFT and training, as is described before, then we finally arrive at the functional that we call MCML. And the exchange enhancement factor of that is here compared to MS2, which is also a rather useful function that we used as our starting guess. So MS2 is what we ran first, and iteratively MS2 was turned into MCML and the famous scan functional. And what is interesting is that our starting guess, MS2, for example, did have this simple behavior that, as you can see on the two upper plots, that the larger the gradient, the stronger the exchange enhancement, while the training to data then showed that, rather similar to the scan functional, that exchange enhancement at some point should decay again. So this is something that actually came out of the data. It was not imposed as an analytical constraint. That's something that came out of the data fitting. But much more interestingly, is actually interesting to look at is actually the performance of this new functional. And as we had aimed for, maybe that's therefore not a surprise, it does outperform all other meta functionals that we tested on chemisorption energies. And this is remarkable because we managed to do so without sacrificing the good description of bulk properties that existing meta functionals have. So our MCML functional is as good as predicting lattice constants as the outstanding scan functional is. And so with that, this is a promising functional for surface chemistry. But since we trained this functional on empirically on data, there's actually now also a way for us to actually predict the uncertainty in our exchange correlation model. So in the interest of time, I'm just going to summarize here that one can use Bayes' theorem basically to reverse engineer the probability of the model giving the data from the probability of getting the data given the model, and vice versa. So what that means is, what we can do is we know, of course, the residual error our MCML function has on our training data. And we can kind of use this, take this as an uncertainty and reverse engineer what kind of perturbations of the MCML function would reproduce this fitting error. And this is shown here. So the black lines are a few fixed alpha snapshots, you could say, of the exchange enhancement factor of the MCML functional. And the orange curves are now an ensemble of perturbations to MCML that reproduce the fitting error. And we can now take, first of all, we can see that, of course, that where the functional is physically constrained, like it's enforced to hit the homogeneous electron gas limit, then there's no uncertainty. there is quite some uncertainty in the very peculiar limit of having a single orbital and no gradient. Of course, that, I mean, if you think about single orbitals in an atom, of course, you won't find much data where you hit this case of having a single orbital and no gradient. So, you know, there's not much training data, and there's indeed a lot of uncertainty what shape the functional could have. Then really what our functional shows there is really just the regularized form of showing the least oscillation in the fit in this limit. This is basically what determines our fit at this point. But we can now take such an ensemble of perturbations to our functional, and we can predict errors on new systems that are unknown to the training. And a very interesting testing case for us here was graphene and nickel. And it's so interesting because there are much higher level of theory simulations on it with the random phase approximation, computationally very expensive, basically a wave function approach to correlation that also works for solids, and which is known to be very accurate for dispersive part. So out here, where as a function of distance between graphene and nickel, where really dispersion forces are dominating, RPA can be assumed to be a very good benchmark. And what you can see in here in the comparison of the different functionals is that, you know, closest to RPA is really our new MCML functional, also in terms of the chemisorption minimum here. Really our new functional is getting as close as possible, but it's still, you know, would be desirable, of course, to have an even better description, or to have a much better description of physisorption. This is insufficient. And the reason that physisorption is described insufficiently is that non-local correlation terms are missing from the functional so far. So explicit non-local van der Waals correlation needs to be added. And this is what we've done next. So we started again with an initial guess for a functional, this time a MetaGTA van der Waals functional. Again, non-self-consistently fitting against most of our data, but now there's a separate, very expensive step to do a semi-reasonably expensive step to self-consistently optimize the van der Waals part with every new functional iteration that we make, so that the van der Waals part in itself is optimized. So it's now an additional third iterative step in this whole loop that needs to be done to simultaneously optimize both the exchange part and the non-local part. And so this is something new here. Typically what one sees is that one optimizes either or, like when one takes an existing functional and one adds van der Waals to it and one optimizes van der Waals so it's optimal for that functional, or the other way around, one has a van der Waals functional and one optimizes the exchange so that it's most compatible with it. So here we've taken the new approach to optimize both simultaneously and with the same importance. And this indeed has then, looking at this important example of graphene and nickel again, led to a functional that does describe, not having seen any of this data in the training, describes the dispersive part that is captured well by the random phase approximation relatively well. So it's definitely very close to that. And it also describes the chemisorption well. And for chemisorption, actually the best estimate that one has for that actual experiment. So one can see that our functional is also very close to the experimental average estimate. So therefore, we believe that this is a very promising functional if both chemisorption and physisorption need to be captured accurately in catalysis or other surface chemistry simulations. And at the same time, that there's a need to describe bulk structures as well at the same time. I think, how am I doing on time?
Indeed, time is over. How much time do you need more?
Oh, I think there's a way for me to summarize this. Okay. This is good. So I mean that means I can save you all, at least for this time, from now machine learning approaches how to address problems when DFT does not have to be slightly optimized, but how to use machine learning to cure problems where DFT entirely fails. And I think I'm just going to very briefly say that one famous example where DFT fundamentally fails is where you, for example, take a sodium chloride dimer and you pull it apart, and any standard DFT approach no matter how far you pull sodium and chlorine apart, they will never become neutral atoms. A little bit of charge of sodium, a little bit of electronic charge of sodium is always going to remain stuck on chlorine. And the problem there is an incorrect relative level alignment, which is due to self-interaction error in DFT, and which means it incorrectly would predict that the sodium chloride dimer would never dissociate. Something that is without self-interaction, like Hartree-Fock, does predict that such a dimer would dissociate. And a more general approach, or a general symptom of DFT self-interaction errors is that DFT cannot properly describe what happens at fractional particle numbers. There, it is really a very simple quantum mechanical average, ensemble average, that dictates that at fractional particle numbers one should have fractional occupation numbers, one should really have a linear dependence of the total energy between integer occupation numbers, as shown here in orange, while DFT gives such a curved line. And there are approaches both on the solid state side to fix this. There's also a very recent paper by a group from Google DeepMind, by Kirkpatrick and others, who train on such fractional particle number problems to actually address the molecular problems shown here to the left. And maybe in a future talk that you might hear from me elsewhere, you could learn more about what one can do with machine learning also to treat more of such problems in solid state chemistry. But in the interest of time, I'm going to jump to my summary. So I'd like to highlight that there's now an increasing number of materials databases with high quality computational data. And of course, that enables in itself that one can basically do research without having to run DFT for oneself anymore, simply looking up relevant material spaces. But it also enables new machine learning approaches. And there I'd like in particular to advocate that there are approaches where one can incorporate both physical analytical model constraints and also high quality experimental data, for which there simply cannot be a higher level of theory than DFT estimates that could guide improvement of DFT. And finally, I'd like to advocate our new functional that is already implemented in the standard library of DFT functionals, libxc. So if you want to try it out, I'd in particular like to acknowledge my collaborators here and there, Kai Trepte, Chris Brown, and Yasheng Maimaiti, who did all the functional development training work, the many benchmark calculations that were needed for that. I'd like to thank the Department of Energy for funding. And I'd like to thank you very much for your attention during my long lecture. For references and further reading, you can take a snapshot of this QR code here or simply type in the short URL. So some of the things that I didn't cover today, for example, like how one can use machine learning to address more fundamental failures of DFT, you will find links in that list that you can check out if you're interested. And in any case, I'm happy now if there's still any time left to take your questions.
So thank you very much for this very nice and comprehensive talk. Now we can unshare the screen to see whether someone raised a hand or no, and take questions. Please ask questions. Send a message through chat button or just using microphone. So questions, please.
Johannes, can I ask?
Absolutely.
Yeah, did you check the performance of this new functional MCML with other systems rather than graphene nickel?
No, of course, one needs something where one has a benchmark, like for example, like the random phase approximation, like something of higher level of theory, so that one knows what one has something that one can compare against. So, and those calculations are so expensive that there's a few strong cases to compare to for that matter. But there are other systems that within the training that we compare to gas phase reaction energies, where it does well on. And unfortunately, for surface chemistry, there's, of course, those are hard experiments. There's so little, but so few data out there that it's hard actually to separate anything out. Of course, there's some regularization or fitting so that we don't overfit to it. But there's not many clear-cut testing cases. At least, of course, over time it will prove, in general, maybe more in an indirect way, how useful it is. But such a strong case of graphene or nickel. I mean, if you know more cases, I'm happy to test this. But that was the most obvious that came up to us. And it's also very interesting because it has both a chemisorption minimum and a physisorption minimum. So it's a very delicate energy balance. That's why it's so hard to get right, and it was a good testing case.
What about band gap calculations? Did you have any tests for that?
We did not. So that was not specifically focused on here. So that this is, we take this to be a total energy functional. So for band gaps, the band gap is not necessarily directly really a fundamental. I mean, DFT in principle is a total energy method. And then one can go ahead, one can take the Kohn-Sham states, which in the first place, one should never interpret as single particle spectra, but it's the best we have to often, so one does it anyway. And then one can apply quasi-particle corrections and get reasonable numbers, like for excitation energies, for quasi-particle excitation energies out of that. I know there are some meta-functionals which mimic such quasi-particle corrections, but I doubt that those are then at the same time very much optimized, like SCAN, for example, for reaction energetics. So I think a good band gap, which is really a quasi-particle properties, is nothing that we were after. So I think it's kind of a somewhat different problem. Okay. Although I know, maybe in correlation, as I mentioned, with the fact that SCAN, for example, somehow does overestimate exchange. I mean, that will open up band gaps. So it can give quote improved band gaps because you have stronger exchange. So but that was not the focus. We did not consider that, and I would not guess it should be performing particularly well on it because it does not lead to exaggerated exchange interaction. So it gives very good magnetic moments. So I guess it doesn't have this artificial exaggerated exchange feature that I believe is in part due for supposedly good band gaps with other approaches.
Yeah, again, can you also compare the performance of GLLB-SC compared to HSC or 6 in terms of band gap calculations? Can we trust GLLB-SC?
Well, I've done some benchmarks and also some ongoing collaborations, and we trust it well. I mean, if you really want to do a high throughput study, then, and maybe also of not just small unit cells, then GW is just too expensive. So I think it's also there maybe the cheapest quasi-particle correction one can have. It's also faster to converge than meta-functional. So I think it's still maybe the fastest approach to quasi-particle corrections. I mean, what worries me a little bit in the GLLB-SC approach that it has a strong dependence on very deep lying energy levels. So I hope they're kind of canceling out. I'm sometimes surprised it works so well, and I like it a lot, but I'm not sure if there's really a fundamental understanding, why it should be performing better or worse than HSE than in hybrids. I mean, certainly GW is better. I mean, that is a proper quasi-particle approach. I mean, HSE, that is just mixing something with a too small band gap with a too large band gap, and of course that mimics a good band gap. But GW is, of course, fundamentally providing quasi-particle corrections, and at a much higher price.
Yeah, thank you.
Oh, thank you.
More question, please. Johannes, we have one question in chat. Can you read it? Yeah.
Oh, okay. And so the question is, what is the next step for an overall improvement of MCML performance for a range of physical and chemical properties? There are some compromises, even with metafunctional. So for MCML, the compromise is that we don't describe atomization energies as well as other approaches. So, what does it cost to atomize a molecule into single atoms, or what does it cost to atomize a solid into single atoms? I mean, for our research, like material science or chemistry, it's not typically not relevant to know what it costs to form something from single atoms, but it's most relevant to know how different stable phases compare to each other. So we don't need to know, what it costs to bind a hydrogen atom relative to a hydrogen atom in gas phase, but rather to H2, because H2 is stable in gas phase, not a single hydrogen atom. So that's why, there are certain things that we did compromise a bit, which of course in my sales pitch didn't quite admit, but now in the answer session, I'm happy to admit that, in future research, I mean, these things can be combined, of course, the training with further corrective approaches. So one could, for example, aim at also training a screened exchange part on top of that, where then the meta-functional would be responsible for suppressing the spurious, exaggerated exchange interactions. That would be a promising direction. And thank you. This is a very good question.
Thank you. More question, please. So it seems that no more questions. So Johannes, please give your concluding remarks, and then, if you don't mind, we can close the session.
Thank you very much. It was my pleasure being part of your seminar series at your institute, and thank you all for listening and for your great questions.
Thank you for accepting our invitation to give this seminar, and we hope that we can meet in person in future when this COVID situation subsides in the world.
That would be wonderful.
So I think so, yeah, certainly. So for the time being, then take care of you, and bye.